Final speaker today is Richard Bradley from the London School of Economics. He's going to talk to us about a little bit different, thinking about some of the sort of philosophical ideas behind UQ.
Okay, thank you. And so the way to get an audience on your side is to have a really bad mishap at the beginning, because everybody sits there and thinks, oh, at least that isn't me. Anyway, so you're probably wondering what on earth is a philosopher doing here amongst all the sort of mathematicians and statisticians, and believe me, I ask that question of myself at times as well. And probably the true answer is that by 4:30 in the afternoon, cognitive resources are at their minimum, and it's still an hour to go before wine, so we could switch off the lights and play some mood music and so on, but why not fill it with something else equally soporific? So that's what I'm going to do. No, I'm not going to do it. So Dave asked me to talk about the philosophy of UQ, and as you probably don't know, there are three kinds of philosophers. There's philosophers who can count and philosophers who can't, and at least they can count. And even those who can, don't really have anything to say about capital UQ. So I'm interpreting this topic a little bit more broadly than sort of the capital UQ look, and I think that's to the good. And so one of the points will be that I hope sort of to keep the wider problems in focus all the time. But there is a lot of common territory here, and so I just want to sort of start out by setting things up in the way in which I'm sort of talking not just as a philosopher, but as somebody who works in decision theory and so interacts with a lot of people in sort of economics, some parts of statistics and so on, but where the sort of problem of uncertainty arises primarily as a problem for a decision maker, and then sort of you think about uncertainty through that lens. But of course, there's a lot of kind of common ground here, and I think the sort of starting point that's in common with capital UQ is this point about the role of scientific models, and rather the predictions that scientific models about decision variables of interest play in policy making. So sea temperature rises, inflation rises, disease spreads, and so on. These are all predictions that we rely on science to provide us for, or decision makers rely on science to provide these predictions. So these models can be very, very sophisticated in the way that they handle uncertainty, and in particular where there's physical or what's sometimes called aleatoric uncertainty, it's the stuff that's sort of structural, if you like. These models will give probabilistic predictions, and if you're a sophisticated policymaker, you can handle that fine, because what you'll do is you'll pick your policies on the basis of their expected benefit, weighing the possible outcomes via these probabilistic predictions. But of course, even though modeling as an activity has grown in importance, but also grown in sophistication with the development of computational mathematical techniques of the kinds that people in this room have developed, modeling has become much, much more sophisticated, but the predictions that you get out of scientific models inevitably remain uncertain for a variety of reasons, and we've already seen these things voiced a number of occasions. The sort of things that people will point to, input or initial conditions are often difficult to measure with any kind of precision. Model parameters have to be estimated sometimes from quite limited data. Of course, the importance of these different things varies from case to case. Sometimes the underlying physical or structural causal relationships are not well known, haven't been studied for a long time. And in many cases, either we know that there are relevant causal factors that have been left out, or we just suspect the so-called Rumsfeldian unknown unknowns. We suspect there are things that we've left out, but we don't know what they are, because if we did, we'd do something about it. So all of these, I think, matter in different kinds of ways, and my aim in this talk will be to describe some of the philosophical approaches out there in the literature, philosophical / decision theoretic approaches to these uncertainties and their management within decision making. So, and in doing so, I'm guided by two what I would regard as platitudes. Platitudes are very important things to sort of state repeatedly. There's a sort of warm, common feeling about yes, that's true. The first is that, they're things that are important but often ignored, I guess that's the thing. The first platitude is that the tools that we use to measure and manage uncertainty should be tailored to the kind of uncertainty involved, as opposed to just using the kinds of tools for measuring and managing uncertainty that you like, most of all, perhaps because you were involved in developing them, and just hammering everything that moves using them. It should be the decision problem that leads the way rather than the technique. Okay, and the second guiding platitude is that we can't assess these tools without thinking about the kind of decisions that they're intended to support. Okay, so everybody agrees with this, but that's sort of what's running through on that all. All right. So let me say a little bit about, so let me sort of put aside some problems just so that I can talk about what the areas that I think are most problematic. So I think largely initial condition and parameter uncertainty, or what I was calling that on the previous slide, can be sort of successfully, if you like, represented by either employing families of input of parameter values or by working with a probability distribution over them. And in fact, that's now sort of increasingly becoming commonplace even amongst policy making in the social sciences, where techniques for handling uncertainty are perhaps at their weakest. So a good example of this, I think I have to, is the inflation fan diagram that is now put out by the Bank of England. So the recognition that the old business of just producing a single prediction for inflation was misleading. The models that are being employed by the Bank of England simply don't support, they don't have enough confidence in their models to be able to, the confidence that they have in their models does not justify issuing a single inflation prediction, and so they've gone on, and this is apparently quite revolutionary in the world. The Bank of England is the trendsetter here in producing intervals of predictions like this. This is what's known as the rivers of blood diagram. Apparently there's a similar thing for GDP growth produced by the OBR that's in black and white and which is known as shades of grey. Not because of the fiscal discipline that is instilled through these diagrams, but apparently because the Treasury lacks colour printers. That's one way of doing it, and of course putting a probability distribution on ranges like that is even more helpful. Here's my sort of ignorant observation of what's going on in a lot of capital UQ work, is that it's largely focused on the measurement of uncertainties in model predictions that are due to initial condition and parameter uncertainties, and tracing those out through the models, but also trying to estimate these things inversely from discrepancies between what the model says is going to happen and what you actually record. So that this is the sort of center of activity is over here, but I think there's a whole lot of stuff that, I mean, it's not kind of completely separate from this at all. I don't want to sort of overdo the thing, but I don't think it in any sense exhausts all the uncertainty that we face, and in particular it doesn't it doesn't exhaust, it doesn't deal with, I think, what I want to term model uncertainty. So what do I mean by that? Well, model uncertainty is just the uncertainty that arises because the empirical evidence that we're dealing with doesn't suffice to fix the various causal, structural, functional relationships between variables or the corresponding parameter values, and sometimes it arises indeed because of the unknown unknowns problem. I mean, sort of wrapping those two together, perhaps unreasonably at this point. So I think you find this all over the place. It's typically concretely manifested in the existence of multiple models. Multiple models are to be found within the scientific community that are all consistent with the data, obviously, because otherwise they would be kicked out. And that's typically the case when the models themselves are producing only probabilistic predictions, because you don't get, there's no single case refutations of models in these kind of cases. And then secondly, by scientific and or scientific disagreement about the status of what might be the standard model within there. So there's a lot of variation between different domains, but I mean, for instance, in climate science is an area where there are lots of models floating around. I mean, there's not necessarily a lot of disagreement about the status of them, but there just are a lot of those models, and there's a little bit of uncertainty about what to do with the fact that there are these different models out there. In earthquake science, which is sort of an area that I've done a little bit of applied work in, applied as in the philosopher's sense of applied, there's really a sort of standard model and a standard way of doing probabilistic hazard assessment within this field. But there's, a very vocal subgroup of earthquake scientists who say none of this should be trusted at all. So it's not that they're competing; it's just they don't trust anything that they have. And then in other areas, like in economics, you see a bit of both. You see multiple models, and nobody trusts any of them, right? And I think these are real phenomena. I mean, I see from the smiles on people's faces that I think many of you have seen this kind of thing going on as well. But it may be much more low-key than in these particular cases. Even if there is a best-fitting model, even if you're in a sort of nicely well-behaved area where there's plentiful data so that you can say with some confidence this is the model that best fits the data, it's still reasonable for modelers and consequently for policymakers to look at a family of models when thinking about what to do about certain things or when thinking about what sort of predictions to adopt, because they might have doubts about the predictions of the best model, even if it's the best fitting one, simply because they know a lot about how that model was put together, and they know that that model idealizes in various kinds of ways. And they suspect that those idealizations will have consequences for the predictions at some points, even if it hasn't fed its way through into the data that they've looked at so far. And that's particularly true in these cases where you're extrapolating to conditions which you haven't been able to observe before. So earthquake science, again, is a typical example. I mean, you're extrapolating effects from you sort of observe a lot of small earthquakes, you observe almost none of the big ones, but so you're forced to make extrapolations. And because you know of the idealizations that you know you're making, you have good reason to distrust, or at least not to have full confidence in the models you're using. And for that reason, it's reasonable for them to consider a range of models that perform tolerably well, but which they know are based on different assumptions. So there's a kind of hedging, scientific hedging that can go on that way. If that's all right, then there's sort of two questions that become immediately pressing. One is if there really is such a thing as model uncertainty that's distinct from the kind of probabilistic, from what's being picked up by probabilistic representations of input and parameter uncertainty. We want to ask how should this be represented and measured, and what implications would any such measure have for policy making? And actually, well, I'll come back to that in a second. So there's three kinds of answers that you find in the sort of philosophical / decision theoretic literature, some of which I think you find in the maths and stats literature as well, but sometimes these terms are not used in exactly the same kind of way, so I'm going to tread carefully. Actually, I should have said right at the beginning, please do ask questions at any point in this thing. I mean, I'm very painfully aware of how vocabularies are different in different disciplines, and it can be that something I say is completely misleading to you, and it's better just to sort it out right at the beginning. Okay, so don't hesitate. So a case in point actually is Bayesianism. So this is a term that's used by people in very different ways. Here I'm just using it in a sort of fuzzy sense as one answer that one might give to the problem of model uncertainty is to say just treat it like any other kind of uncertainty. Try and get a probability onto the relevant space, and then use probabilistic averaging to generate your predictions. And so I think there's a lot of people within the philosophical decision theoretic community who think, at the end of the day, when we've finished agonizing about, that's going to be the best answer to this, and so we can go back to doing pretty much what we've been doing in the past. But there's at least one other prominent, let's say, an answer that's now becoming much more prominent in the literature, which is this what I'm calling imprecise probabilism. And this is the idea is that you should somehow represent your uncertainty by working with families of probabilistic predictions rather than single ones. I'll come to that in a second. And then this third view, which I have to admit is my own, and that's why it's sneaked in here, is that that's still not good enough, and that we need something like a confidence grading of these projections to get a proper handle on what's going here. So for the rest of this talk, I'm going to sort of work my way through these three answers, partly sort of expository, partly sort of critically, to sort of I can't resist, and it's built into being a philosopher to sort of throw my own opinions in all the way along, but I think that's the way it goes. Okay, so just a word about sort of model averaging, and in particular Bayesian model averaging. It's a very large topic, and what I'm going to say, I'm sure, is very contentious, but I would like at least to just set out why I think what's sort of attractive about doing some kind of model averaging when you're not too sure about what the best model is, or when there's a range of models that you think are credible, and what I think is not right about doing that. Maybe we can come back to some of this in the questions if you've violently opposed to what I say. So the sort of general idea of model averaging, and I'm sure it's familiar to all of you, is just to try and give each model a score which reflects how good it is. So sort of canonically, this will be done in terms of its fit with the data. So this is I see as one of the sort of points at which sort of work about model discrepancy becomes very important, because that's what a score like that might feed into. But you might also want to throw in, you might also want the score to be sensitive to how simple the model is, what it's explaining, and all sorts of other virtues of a model that you might want to use to score it if you want to do something a little less standard. In principle, it's always the same, and then you model the model's predictions. So maybe you're interested in sea temperature rises, so you've looked at all these climate models, scored them, and then you average the predictions coming out of these different models to produce an average probability distribution over the predictions, over the prediction variables. And then again, yeah, please. Yeah.
You may come to it later, of course. When you are averaging,
Yeah.
are you talking like some kind of arithmetic mean value, what possibly weighted?
I mean, in this case, I simply mean is you're thinking each model is giving you a probability for a set of variables that you're. So let's take sea temperature. It's telling you what the probability that the sea temperature rise is. You know, what's the probability that it's over, say, 1 degree, and you're taking that for each of those models, and then you just use the score that you've given to the model to weight each of those, and then you just then you're doing the arithmetic mean.
The result is a weighted arithmetic mean.
That's right, and so you've got to be sure that it's all probabilistically consistent, and I'll come to that in a second.
Well,
but
there is a kind of extreme situation involved there, where most of the models give relatively similar results, but one or two with possibly relatively low probabilities give very large results.
Yeah,
And their contribution to the arithmetic mean
might swamp it.
could be enormous.
Yeah, that's right. That's right. That's right. So
It's like you know, consider our average income.
Yeah.
And if Bill Gates walks into the room,
that's right. But I mean, that may not be wrong, right? I mean, if you think that if you think that the model is credible, it's credible enough to have got it to be sort of it's credible enough that you're giving it consideration. And now you've given it a score, and its score is not appreciably lower than the other ones. Then you need to take into account somewhere that there's this credible possibility that sea temperature rises are going to be very, very high.
yeah, but the point that argument leads on to is that it might be, so to speak, more reliable to look at something like the median
Oh yeah.
than the mean.
Yeah. Okay. No, that's right. So the points that I want to make is not going to be sensed. Yeah, that's right. I mean, you might not want to use the mean. You might want to look at other ways of aggregating the data in some kind of way. My main point is going to be about whether you want to do any sort of aggregation at all, or whether you want to just sort of say, look, here's the range. Here's a model that tells us there's a lot is going to happen, and here's a whole bunch of models that tell us very little is going to happen. And some people would say that's where you stop talking because we can't do anything more with it. So that's the sort of level of sophistication that I'm pitching this at.
Yeah. Could have simplified this perhaps, this discussion,
Yeah.
because the misleading thing here is that in Bayesian model averaging, you don't average the predictions, you average just the probabilities.
Yeah.
There's no issue of needing to take
Yeah.
the median, it's just averaging the probability.
That's right. Okay, and the predictions that I'm talking about here are probabilistic. I'm thinking of the prediction as the probability distribution over the variables. In which
There's never an extreme
There's
value there, it's always between 0 and 1.
Thank you. Thank you. That's fair. Okay, so that's lots of sort of things one can argue about the details here, but the sort of general idea here is you want to get back to, in effect, a single prediction, single probability distribution. And the reason why you want to get back to that is because decision makers know what to do with it. Once they've got a probability distribution over the sea temperature rises, then they can maximize expected benefit of policies relative to those probabilities. So that's the big advantage of doing that, and I think it's an important benefit of this approach. However, there are philosophical issues that I think are important here. So one, of course, is just what is the meaning of these model scores, and hence of any kind of aggregate based on them. Right? And then, and in particular, so if you want to do Bayesian model averaging, you're going to need to be able to interpret them as probabilistic measures of uncertainty, and it's a question of what's involved in that. So here's what I think are some problems for model averaging. So if you want to do it in a probabilistically consistent way, then you need to average over a partition of models. I mean, the space of models that you consider needs to have the right kind of properties. But that's never what we have in practice. In practice, what we have is a bunch of models that are neither exhaustive nor mutually exclusive. In fact, what the relationship between them is often very, very complicated from a logical point of view. And so you can't just do probabilistic averaging over them because you're not dealing with a proper Boolean algebra to start with. So I mean, that's maybe a practical problem, but I think it's a serious practical problem. A little bit more fundamental is this thought that, look, all models are false. Right? Yeah. So whatever these probabilities are, they're not measuring probability of truth. And, you know, so it's sort of not clear what these scores are supposed to be picking out at all. And the third one, which to me is really the most important here, is that it misses what we're doing when we're modeling. I mean, very often different models are good for different things. So we shouldn't sort of think of models as having a single score. If anything, they have a sort of use-relative scoring might be appropriate to these things. So the weight we would want to give to a model will depend on the claim or prediction that we're interested in. But if we have to rescore every time we look at a sort of different kind of prediction, then there's very little to be gained from giving the models scores. We should rather just look at the predictions themselves and ask sort of how much support does each of these predictions get, and then think of these models as providing support for the predictions, not as things that you want to score independently. So the conclusion, the sort of informally argued for conclusion here is I think that probabilistic model averaging doesn't adequately capture the role that models play in supporting forecasting. They're not there to provide sort of true statements about the world that one can then average over. Okay, so as I said, we can. There may be some of the youngsters who feel that I've not given this a fair shot, but we can kind of understand.
Doesn't, right?
Doesn't, yeah.
Okay.
Doesn't. Important, yes. Yeah. Okay. So now we may start with a toy situation to kind of motivate these other views. This is, for those of you who know this literature, is just a version of the Ellsberg paradox. And the idea here is to sort of model models by urns. So we think that we have here, we have before us 3 urns that contain 100 balls. The models are not modeled by the urns. The models are modeled by our theories about what's in the urns. Okay. So we have in the front of us 3 urns containing, let's say, 100 balls, and these urns are different.
100 balls each.
In each of the urns is 100 balls. Urn A contains, we know, half black, half white, and this is to model a situation that I will call a situation of risk. The second urn, B, contains, we know, only black and white balls, but we have no information whatsoever about the proportions of them. And this will be my model of what's sometimes called in the literature ambiguity. The third urn contains balls. That's all we know. There might be some black and white ones in there, we don't know. Right? And this is what I will use to model what I'm going to call severe uncertainty. And so this basically the situation is when we don't know, reality is probabilistically, but we know exactly, we have all the information that we require about that probabilistic structure. Second case is we lack probabilistic information. Third case is we don't even know what the state space looks like. And now, suppose that you can bet on the draw of either a black or a white ball from any one of these urns. Right? So what's on offer are things like a draw of a white ball from urn A, a draw of a black ball from urn C. Right? These are all bets that, and let's, suppose the bet pays £1 and it costs 50p or 40p to divide or something like that. It doesn't really matter what the pricing is. And you sort of think about what bets what your preferences over such bets might be. Okay, so in particular, would you prefer to bet on a white ball or a black ball from urn A, a white ball or a black ball from urn B, and so on? Would you prefer to bet on a white ball from urn A or from a white ball from, or a white ball from urn B, or from urn C. Even if you have seen this before, just give it a little bit of thought and think. So a very common set of betting preferences that comes out in the experimental literature is that pretty much everybody is indifferent. Once you fix the urn, pretty much everybody is indifferent between betting on white or black, except for those who have sort of recherche colour preferences. But on the whole, there doesn't seem to be any reason preferring to bet one way or another. But quite robustly, people prefer to bet on balls drawn from the first urn than from the second urn. And, I mean, there's a lot of evidence for that. And there's a little bit of evidence that people prefer to bet on balls drawn from the second urn over balls drawn from the third. These preferences are completely incompatible with Bayesianism in the sense in which I use the word, and by that I mean it's incompatible with the view that what people are doing when they price these bets is they're thinking about the expected benefit relative to some probability measure that they've put on those ball draws. Right? Because if you have those first set of preferences, you're revealing, as it were, that you regard a draw of black and white as equal from all three urns. And equal just means probability 1/2. Well, if it's probability 1/2, you cannot have the preferences 2 and 3 in these cases if you're maximizing expected benefit. So, I mean, are there people in this room who have preferences like that? Like the common ones, or would admit to preferences? No. Okay, so you'll just have to regard it as a paradox about ordinary human beings.
I would fall for 3.
Perhaps, okay. Not 2, that's the very robust one. So how are these to be explained? So this is the sort of thing you get from people when you ask them. They say, well, there's more uncertainty regarding the draws from urn B than there's from urn A. Why? Well, in urn A I know what the probabilities are. In urn B I don't. That's the sort of thing that they'll say to you. Or they'll say, that's repeating what they're saying. I know what the probability of a white ball being drawn from urn A is. I don't know what the probability of a draw of white from ball B and urn B and ball C. Okay. So the upshot seems, at least if we take the behavior of people not in this room as a guide to perception of uncertainty, but I think in this case the perception is tracking something real. Merely giving the probability of a white ball doesn't give us a representation of all the uncertainty that people face in their decision making, even in this very, very toy situation where there are symmetries all over the place.
Sorry, I think you're not saying as much about these latter two. When you ask about those choices, you can start making up scenarios that make it seem less likely, even whether there's any evidence of it or not. You have a mental game that you're playing with yourself.
I don't see how it could be both more probable that you're going to get a white ball from urn A than you get a white ball from urn B, and that they can.
You're pessimistic, and there are green balls in these other urns, and you imagine.
No, but there's no green balls in the second urn. I mean, so that, forget about line 3 here, because that's a bit more complicated. Just line 2. We know there are only black and white balls here.
If you're pessimistic, you can imagine.
You ask the question.
Well, the way you ask it is just the way that I did. I ask you for your betting preferences.
Yeah, because at that point, I mean, if you would just ask question 2, and then the person who's asking it to you has actually stacked, has chosen how many balls to put in urn B in order to win against you. Are you betting against the person who constructed urn B?
I'm asking for your betting preferences, actually. So there aren't. So one thing you might complain is there aren't any real financial incentives built into this presentation, so you can say what you like. But that's to sort of guard against this. But look, people might, but honestly, people are not that suspicious. If you put a lot of money on the table, they'll get suspicious. But if you're asking just what's your preferences over these things, I think I look at these things, I can't give an honest answer. I have those preferences. I'd rather bet on the urn where I know what the probabilities are.
Why should it be expected utility people are
going after.
No, that's true. That's just to sort of make it nice and simple here. I mean, so one lesson that people will take away from this is, but there's no way of rationalizing this in terms of people working with a single probabilistic measure of uncertainty on any decision rule that's out there. So you can change the decision rule, but you won't change the conclusion easily. So I'm getting a question over there, and then I'll come back.
I was just going to ask about the personal biases, the decision biases that you get depending on the order in which the choices are presented, and whether or not actually.
Yeah. So I should have been a whole lot more careful. So the way this is, you do this if you do this carefully, is you make sure that you give people the opportunity. I mean, you don't sort of focus them on either white or black. You say, look, here's the possibilities. You can choose between these two, or you can choose between these two with the black version.
Flip A, B, and C, though.
That's different.
It has to be in order, yes, but
Present C first.
Or present C first, yes. I do not personally believe that we would get such robust. We could. 1 and 2 is robustly true about a quarter of the population, and there's been lots and lots. I do not believe that can be explained by details of the experimental setup and the order and so on. People have done this in different countries with slightly different versions and so on. It's what you get, and I mean, part of the plausibility of that is that these sort of answers, even if you don't agree with these answers, I think you understand what people mean when they say these things. Right? I mean, it looks like a not irrational thing to worry about when confronting these urns. Is that in the one case you sort of know something more than you know in the other case, and if you prefer to bet under conditions where you know more, then it's not unreasonable to have these preferences. Anyway, that's
applying, as it were, quasi-Bayesian issue regarding urn B. That if you bet on black for urn B, you are more likely to win if black is the majority colour, but less likely to win if white is the majority.
Yeah, right.
So if you have no idea whatever which is the majority colour, you might then, in my view, blindly apply Bayesian ignorance prior and give them equal probability.
You might indeed.
In which case, your betting on black from urn B is equivalent to betting on black from urn A.
Yes, that's right. So if you're a Bayesian, you shouldn't have these preferences.
That's right.
Yeah. No, I'm completely agree. That's what I say. These preferences are incompatible with Bayesianism. I mean, I'm completely agreement. So in the literature that I'm sort of drawing this from, this is usually trotted out as the reason why you should abandon Bayesianism. I mean, not just this, but this is the thing that's supposed to warm you up to that idea, because you look at these preferences, you think this is not completely crazy, right? So if it's not completely crazy, Bayesianism's claim to encapsulate the boundaries of what is rational now looks less secure. I think the best I can hope for is to sort of seed that thought. I assure you, sane people in other disciplines take this quite seriously.
Quick question.
Yes.
As a Bayesian.
Yes.
It's also true that more than a quarter of the population can't do arithmetic.
Yeah.
Arithmetic.
Not the same quarter, though. Some quite mathsy economists have these preferences. I mean, perhaps the situation is too tight to be highly motivating, but suppose it's a sort of medical operation, right? You've got two procedures, right? And you ask, what's the survival rate from these two things? Right. Case 1, look, we've performed this operation a lot of times and 50% of the patients survive. Right? And those who don't have the operation, they will die, something like that. So just to get a sense of operation 2, we know nothing, right? So here's my flat prior, I do the Bayesian thing, so it's 50-50. My ignorance prior gives me 50-50. Which operation would you sign up for.
None of them.
So I don't understand the second example. So you're saying that 50% of the people survive in the first case, but no one's ever done the operation in the second case? I get
There's
it.
no data about it.
Yeah. So the second operation is NB, right?
Yeah.
So there are only survivors and dyers,
Yeah.
right? But in unknown proportions,
Yeah.
right? So that's the situation. And the first situation is where we know 50% of people survive. Which procedure would you prefer to undergo? Yeah, probably. Preference is relative. I didn't say you like either of them. I mean, or make it a side effect. It doesn't matter.
But couldn't you argue that people have different modified priors, so it's not irrational, but it's a personal experience? Like, I had a doctor who was very confident that this treatment would work, and he failed, so I don't trust confident doctors, so I have to... I trust a person who doesn't know anything, and vice versa. So in this example, maybe one person has been cheated a lot by gamblers, and so
Yeah.
he likes to have very little uncertainty and very little freedom of design on the person who gives him this trade. So I don't think I don't quite see why this disproves Bayesianism, but I think it fails to capture the priors we have as an individual. Maybe that's wrong.
I think Bayesianism is an enormously flexible framework, and clever people can use it to rationalize pretty much anything if they want to. But I just don't find that a very plausible account of what's going on here. I mean, no doubt some people have very idiosyncratic views about gambling situations. But a quarter of the population, I do this with my students robustly every year. I mean, they're a mix. They come from all over the world. They're very different people. I just don't believe that they all have the sort of...
Can you not go back to Bayesianism by assuming some asymmetric loss functions,
Yeah, you can. You can. I mean,
that would solve quite a lot.
Yeah. There are things you can do to rationalize this. I'm not pretending that this is a knockdown argument. As I say, clever people, and in fact, I think this problem is too toy, and there are too many symmetries around, which can... what I do want you to get some sense of is I think that there is a difference in in finding yourself. So what I want to get out here is one can be in two situations characterized by rather different levels of information. And in both of those situations, your best estimate for some outcome is, say, 50%. Right, so pick anything you like. It's just, in both cases, clever people have done the best they can, and they come up with the estimate 50% in these two situations. Is there anything to be said that is decision relevant about the difference between those situations? And I think the answer is patently yes. There is. In the first case, where there's a lot of information, you can be more secure in making those decisions because you're more secure about the estimates that you're... I mean, I'm using this word secure now because I'm looking for some word that doesn't have technical meaning. But it's, that's you can with greater... I'm going to use the word confidence because that's what I'm going to use. You can with greater confidence go ahead and make a decision in the first situation than you can in the second situation. Okay, that's all that I need at this point, is to say you are in a different position in those cases, and I will argue in a few minutes that has some decision relevance.
Might I introduce another, as it were, quasi-Bayesian factor into this? That one can divide Bayesianism broadly into two. One is what you might call abstract Bayesianism, where you apply formal principles, say of Hickman's prior or Jeffrey's type prior or whatever.
Yeah.
The other end, which is the one I favour if I'm going to be Bayesian at all, is empirical Bayesianism, where you have independent evidence about what the prior distribution should be.
Yeah. But then wouldn't you just want to say that I just don't want to deal with earn B?
Yes.
Yeah, okay, but that's fine. But then you're just saying there's some situations in which I can be a Bayesian and there's some situations in which I can't. Which is perhaps makes, I mean, it's a more extreme view than mine. Mine is that sort of, we need to be sensitive to some other features of the situation than just the ones that Bayesian acknowledges. And then I think we're broadly on the same track. If there was one more question, and then I think I will move on, because otherwise I'll get nothing.
You probably should move on, but I really don't see the difference between A and B. I'm a Bayesian. Just 50% is 50%, so what does it matter? Your argument for saying that we should consider a difference between A and B is that 25% of people do so. I don't see that is a good reason. And essentially what you're talking about is uncertainty of uncertainty, but you can just integrate out the highest level and come back to your 50%.
Yeah, okay, so it's the unwillingness to do the last bit that characterizes this quarter, of course. No, I don't, just to be very clear, I'm not saying that these are the preferences you should have. Bayesians are rational people.
Thank you.
I just, the question is every rational person a Bayesian? That's the side that I'm trying to.
Good question.
Okay. And on that note, I'm going to press on a little bit. You know. Do I get to go 10 minutes late for being so? Okay. Right. So in the literature, one of the prominent responses to this is to say, okay, well, what's happening in the second ERN case is when you don't know what the probability is, you should just look at the whole family of probabilities that are consistent with the evidence that you have. In the case of ERN B, you have no evidence, so you should work with the full family of possible probability distributions. And this is a view that I'm going to call imprecise probabilism. It's now, it's been advocated in statistics by Peter Wally, Gert de Koeman, and others. In economics by most prominently Isaac Gilboa and David Schmeidler, and in philosophy by Isaac Levi and James Joyce, and a number of other people. It's a sort of quite a trendy area at the moment. So here, the idea here is that this should apply in situations in which information is too sparse to determine a unique probability for all the things that we're interested in. And then the idea is that you work, instead of working with a single probability, you work with a sort of set of admissible probabilities, where the size of the set of admissible probabilities implicitly expresses the extent of your uncertainty about what the true probability distribution is. Okay, that's the sort of informal thought here. So you're getting, as you see now, sort of a kind of an implicit measure for model uncertainty. So if you're thinking of these probability distributions as being generated by models, you could replace you could sort of measure your model uncertainty by the size of the family of probability distributions that you think are supported by the models that are around at the time. And it's sort of intuitively here, the idea is that the predictions that are supported by all the probability distributions in the family that you're working with are to be regarded as secure, right? So these could be a relatively homogeneous bunch of probability distributions. They sort of agree on most stuff, but disagree parts of them. Then there'll be lots of things that you're secure about. Might be that it's an extremely heterogeneous bunch of these things, and there'll be very little that you'll be able to say with any security. And in the latter case, well, in either of these cases, so one of the arguments with thinking about this is that licenses a kind of caution in the decision making which wouldn't be licensed if you were a Bayesian, because you can ask your decision makers, or the decision makers can seek to do this, to find options that are robustly beneficial over all the probability distributions that are regarded as admissible. Right? So instead of just simply maximizing expected benefit, you sort of look at what the expected benefit of your policies are relative to every one of the probability distributions that you admit, and then you say, look, some of these policies are good, picking some subset of them, others are good if I pick other subsets. The thing that I'm going to do is the one that is robustly good enough. And there's going to have to be some sort of satisfying notion in the background. Okay, and so you can robustly and cautiously decide on that basis. So I think this approach too faces some rather fundamental and difficult questions. And the main one is really just how this set of probability distributions is supposed to be generated. I mean, what determines the ones that you adopt? And in particular, I mean, I think that the important question here is it a scientific question, what the set is that you should look at, or is it something that's, you know, to be settled by the decision maker as a function of their tastes? So if you're a more cautious kind of decision maker, you work with larger ones. If you're a adventurous type, you go Bayesian and pick one. Right? So that's the kind of question here. And you get a variety of answers in the literature, and none of which except for the one except for mine, none of which are completely satisfactory. So one very common answer you get in the philosophical literature is the sort of the virtuous answer, which is that you should not rule out any probabilities that are not ruled out by the evidence that you have before you. Where ruled out means, it's just not consistent with the evidence. So typically if you do that, you're going to end up working with rather large families of probability distributions. And so you're going to end up being an extremely cautious decision maker, perhaps ridiculously cautious decision maker if you really follow them. But anyway, that's a very sort of prominent answer that you find in the literature. Economists tend to avoid the question, but implicitly what economists tend to think is that it's an issue that should be settled by the tastes of the decision maker, and something that you then you as the scientist elicit through the preferences by looking at the preferences of the decision maker. So these are diametrically opposite answers to this question. So if you see this term ambiguity aversion, it's bandied around a lot in the economics literature. This is supposed to pick out a taste characteristic of decision makers for avoiding situations in which you don't know what the probabilities are. That's something that would be revealed in your preferences for betting over risky earns rather than ambiguous earns, for instance. And that's supposed to, the presence of ambiguity aversion is supposed to alert us to the fact that a set of probability distributions is being admitted, but whether or not that's... Now, I mean, that just seems to me a way of avoiding the normative question. Yeah.
Does this not allow the case where the decision maker ignores the evidence and chooses that action that pleases him?
Look, it really depends on who... economists are are very reluctant to ever tell people what to do, and so they would say, no, that's fine. You can ignore the evidence. All I'm interested in is whether your preferences are consistent, and if they're consistent, then I can model them in a certain kind of way. And it'll be the way I'll end up modeling you as an economist would be exactly the same as if you were picking your probabilities in the right kind of way with reference to the evidence. They won't say anything more than that. But of course, I mean, informally, the thought is that everybody's doing the best they can with the evidence that's before them, right? I mean, none of this is supposed to be motivated by the idea that some people are being irresponsible in any kind of way. They're looking at the evidence, and some people are saying the evidence is not strong enough for me to feel secure in these predictions, and other people are saying, no, I'm enough familiarity with this area, so I'm happy to go for a very precise prediction. And the question is, what's the difference between these two people? It's not about the evidence that they have, so what's the difference? Is it just a matter of taste, or is there something that we should acknowledge as scientists that's different about this situation? And so I want to suggest that there's a very obvious answer here, that we should be picking these families of probability distributions on the basis of the amount of the confidence we need in the predictions that they support to go ahead and make the decision that we want to make. And this will vary from decision to decision. If I go into the supermarket and I want to buy a can of baked beans, and I don't really have much information about which one of these cans in front of me contains really the best set of baked beans in front of me, I'm really not going to be worried about whether I have a precise answer to the question of which is the best can, because there's not a lot at stake in that decision. On the other hand, if I'm thinking about siting a nuclear power plant, I think I need to have a lot of confidence in the predictions that are coming out of the models that I'm doing in order to go ahead with that decision, in order to make that decision. Right? So in those cases, when you say how big should that family of probability distributions that you admit into consideration, the answer is very large, because there's a lot at stake in this thing. So this notion of confidence is supposed to serve as the bridge between the uncertainty, which is something that's scientifically measurable, and the decision purposes that are driving the use of models in the first place. So in the sort of last few minutes, I'll try and cash that answer out a little bit more. So here's another little paradox which will help motivate what's going on here. So sometimes known as the paradox of ideal evidence. So we're back to the urns. So now suppose, and this is, most of you will be less moved by this because I think you were all Bayesians in the first place anyway. This is supposed to be a problem now for those who've gone imprecise in response to the problem. But follow me through the dialectic nonetheless. So now we're thinking about earn B. So that's where we start off. We know nothing about the colors of we know it's black or white. We don't know anything about the proportions. And then we start doing some sampling with replacement. There are only 100 balls, and we do this 1,000 times, and we find that approximately 50% of the balls are white. Now we've got tons and tons of evidence, right? So maybe we started out thinking it was 50-50 white or black, and now we've done all the sampling. At the end of it, what's the probability of white? It's still 50%, right? So nothing much has changed now. Probability judgments, but our confidence in those judgments will have changed a lot as a result of all that sampling. Okay, and this change is what I say should be represented in should feature in our representation of our uncertainty. It's not a new point, actually. Keynes made this point a long time ago in his treatise on probability, where he's making this point that probability and weight of evidence, what he calls weight of evidence, are distinct things. So he says as the relevant evidence at our disposal increases, the magnitude of the probability of the argument, and this is the probability of the white or black balls in this case, may decrease or increase. Don't know. But something seems to have increased in either case. We have a more substantial basis on which to rest our conclusion. I express this by saying that an accession of new evidence increases the weight of an argument. So a weight of an argument, and you can throw in, by that, Keynes is not so clear about this, but what I understand that to mean is something, the quantity, the quality of the data that we have, our skill in using them, and perhaps various other factors. All of those contribute to the confidence we have in our findings. Right? So what our findings are may change, they may not change, but our confidence in those findings may go up. So evidence is playing two different roles here, right? It's playing one role is in telling us what our findings should be, and another role in telling us how much confidence we should have in those findings. All right, so yeah, nearly done.
Can we correct the slide?
Yeah.
Is it not more precise to say that although our probability judgments don't change, our confidence in our frequency judgments change? The frequency falls in the urn.
Well, I agree that there may be reasons for preferring that locution. I think we'd have to work our way right through. We have to get the details of the uncertainty to settle it. But I see where you're driving at, yeah. And I think it's a reasonable point. Yeah. I'm not going to be that careful at the moment. I just want to get out the main.
Just a quick question.
Yeah.
So let's just take this test you're making there, and maybe not take 1,000.
Mm-hmm.
And we know that the probability that we might get a 60-40, even if the reality is 50-50, is high.
Yeah.
I think a lot of people will then start to switch their allegiance and go for B instead of A, because exactly what you're saying, it increases the weight of the argument, but in reality it hasn't increased the weight of the argument.
So A was supposed to be kind of the end point of this sampling. I don't have any definite views about how much sampling is enough for us to now call it as a sort of known proportion. I think that's something that's worth testing, and it hasn't been done, interestingly. I mean, there's all this mountains of experimental evidence comparing earn A and earn B, but absolutely nothing tracking people's changes through sampling, which looks like you're driving it from one situation to the other. So it's just an open question about what will actually happen. But I mean, still, the known proportion case should be the one in which you have the most confidence, at least theoretically. So these pictures here are supposed to sort of give you some idea of what's going on here. So broadly, your confidence in a finding is going to be inversely related to its specificity. So these sort of intervals here are sort of very non-specific probabilistic predictions. So here's a sort of thought about what might go on during this sampling. I mean, it's just a kind of toy picture of how somebody's mind is going on. So you might start out in a situation in which you think, look, my best estimate is that the probability of white is somewhere between 0.5 and 0.75. That's about as specific as I'm prepared to sort of get on this thing, because I know nothing at the beginning. My confidence even in that interval is pretty low. But if we push it out to sort of 0.1 to 0.9, then my confidence is up to medium that the correct probability is in that interval. And of course, if we go all the way to the 0-1 interval, then I have very high confidence, maximum confidence that I've got the truth caught within my very non-specific prediction. Right? But as we do the sampling, these things are going to start changing. So what happens is, as the weight of evidence increases, these intervals start to shrink. So in other words, at low confidence, I have low confidence, but in something that's more specific. And if we go up to medium, and conversely, if we look at this interval, the 0.5 to 0.75, that started out as being something that I would endorse with low confidence, but after, say, 100 draws, I'm willing to endorse it with medium confidence. And then by the time I've got 1,000 draws, it's well into the high confidence zone. So as the sampling is going on, they're not really two things, it's the same thing that's going on, but you can look at it from two different directions. On the one hand, if you fix on the confidence levels, the specificity of the predictions supported at that confidence level changes. You're going to get more and more specific at that confidence level. Or on the other hand, if you focus on an interval, a particular prediction interval, it's going to move from potentially a low confidence situation into you're going to have more and more confidence in that interval with more and more sampling, and of course some will drop out entirely. So that's a sort of toy picture, I think, of what's going on in that thing, and it gives you a kind of explanation for why you get the kind of decision relativity of the kind of intervals that you want to fix in for decision purposes. Because if you make, well, let me just come to that. That's the last thing. So I'll finish on this. So what does this have to tell us about model uncertainty? Well, so the idea here is that we had three views, right? We had one view, which is that at the end of the day, even if there's model uncertainty, what you want to pick out is a single prediction or a single model, if you like, using the full Bayesian apparatus in order to get you there. Then the imprecise probabilist said, no, we want to be more cautious than that. We want to look at some family around our best estimate, and that will give us some sort of robustness in our decision making. Okay, and then I asked the question, well, what picks that? How do we pick that family? Here's the answer: we don't pick that family. We just look at we try and get a nested structure like this as we look at families of families, right? And what distinguishes these families is a sort of confidence grading of them. As these families get bigger, we have more and more confidence in it. So that's what I think scientific representations of uncertainty ought to end up with. That's what they should give policymakers, is a nested family like that. And scientists can do that because they can assess both, what our best estimate is on the basis of the evidence, and tell the policymaker through a diagram like this something about the trade-off between specificity and confidence that their domain is characterized by. Right? Domains where there's lots and lots of evidence, you'll start out in a relatively high confidence situation, so the loss of specificity won't buy you much. In domains in which there's very little evidence, by going less and less precise, you'll gain a lot of confidence. So what does the decision maker do? And I'll finish on that. Well, the decision maker, and here I'm just going to point you to a decision rule that's really been thought through more carefully by a guy called Brian Hill. And his recommendation is that you look for each decision. You determine on the basis of the decision problem that you're facing how much is at stake. And then on the basis of how much is at stake, you determine how much confidence you need in order to make that decision. And then based on how much confidence you require, you fix on these probability families that you're going to work with in your decision making. So if the stakes are very high, you'll want to look at a very large family. If the stakes are very low, you can look at a very, very small family. Perhaps at the limit, you can just look at a singleton. So the first thing is your decision problem tells you which family to look at. Right? It's telling you which family you want your decision making to be robust with respect to, right? And then you employ some rule of robust decision making at that point. And there are various ones that you can pull to. Okay, so that's the decision side. That's in a sense not the side that sort of we're concerned with here. The point is that uncertainty representations like this, I think, are worth thinking about, because they're things that are useful to decision makers. They allow decision makers to calibrate their decision making, not just to what the best estimate of the situation is, but to what the terrain around those best estimates looks like as well. And that, of course, is a matter of the evidence in the field. Okay, so I'll leave it there. Condemnations.
Michael.
Yeah. So it's interesting if you start sampling. I mean, how? Because I don't even understand it at the first level. I mean, so they're saying that somebody prefers they prefer white in A to white in B.
Yeah.
They prefer black in A to black in B.
Yeah.
So presumably they prefer white in A and black in A to white in B and black in B.
Well, not necessarily. You know,
They don't. That's because you are now revealing to them, effectively, the Bayesian argument.
so it's yeah. So what your point is something that's it's well. One thing that happens to you if you have these preferences is that you can be caught in money pump-like situations. So, and indeed, that's so. One of the things that Bayesians say is, look, sure, people have these preferences, but it's very bad for you to have preferences like that.
Well, usually you money pump them out of it.
Well, or you can money pump them out of it if it's possible. And many of these cases are. But look, I think that's overstating. I think these preferences are like having expensive. Well, here's a better example. You know, Monday morning, I often think, you know, it'd be nice to go to a concert on Saturday, right? And I very enthusiastically go off and buy tickets. And by Saturday morning, I'm thinking, oh, this has been a hard week. I wish I wasn't going to the. Somebody could money pump me.
Yeah.
If they knew my preferences. Would that mean that I'm irrational? No, it would mean that I have preferences which enable other people to make money out of me.
Yeah.
And that's the way I feel about these earned preferences too. If you have these preferences for draws from B over A, you can be pumped.
These are not subtle, complicated pumps.
No, noise concert tickets on Monday and concert tickets on...
but really that's, I mean, if you knew that someone was going to do that, and every week they did it, every week you ended up with money, you say, wait a minute.
I would stop dealing with that person. I would change my preferences. I'd stop dealing with them. And it's exactly the same with the earned preferences. I would still prefer the bets that I just wouldn't talk to you anymore because I know what you're going to do to me. That's the rational response. No, the broad point here is I don't think pragmatic vulnerability settles the rationality question.
It does mean that your decision making, you are going to end up making decisions which make you sure losing.
If they have certain sequential structures,
yes.
That's true.
And that's the fundamental point.
But not with
I have a completely classical statistics take on this. So for earn 2, I'm going to toss a coin about whether to go for black or white, which makes earn 2 identical to earn 1. Yeah. Then as data arrives, my job as a classical statistician is to improve that bet. And that you can do just with classical coverage probability. So I agree with everything you say, except you can put a classical statistical...
That's probably true, and I reveal my Bayesian origins by... So, you know, on an autobiographical note, I was a teenage Bayesian, and I thought everybody who was rational would be a Bayesian. I didn't know why people did classical statistics. I think I understand now why they do.
This is the sort of argument which would push you back towards your grandfather did.
Yeah, right.
I mean, the earn example again. So if you say this is rational behavior and not rational behavior, I don't think that's the right phrasing. I mean, if you say this is what comes out across cultures and different people, I think we have to accept it. It's biological reality. So why are people deciding like that? I think it's an evolutionary question or so.
Well, the reason why I do ask the rationality question is for the sort of reasons Michael has brought up here, is that we do want to worry about whether people adopt attitudes which will inevitably lead them to situations which, by their own lights, they regard as worse. And so I think that there is something about the rationality of these preferences that's at stake when you think about it that kind of way. So I was sort of not wanting to accept it, but I accept the force of the argument. But also in the end, if you're a policymaker and you know that the people you're taking actions on behalf of other people, and you know that people have these uncertainty attitudes, you also have to take a view about whether you're going to be paternalistic and ignore them. So that's not good for you to have those kind of attitudes. I'm going to sort of do things on your behalf which aren't sensitive to these things or not. And so I think you're going to have to ask evaluative questions about these.
You're totally overconfident what a policymaker can decide or not.
The ideal policy.
One last question, if there is one.
Okay, to come back to Bayesian ignorance trials, the
Yeah.
issue which actually puts me off automatic Bayesianism, and that is the so-called concept of the ignorance prior. Say you've got a parameter, a probability between 0 and 1, and you're completely ignorant about this. The standard Bayesian reaction is to say put a uniform distribution.
Yeah.
But if you are completely ignorant about the value of that, you are just as completely ignorant about any nonlinear uniform transformation, increasing transformation, monotonic transformation of it. And so you should also put a uniform prior on that. You can't put it on both.
Yep. I agree.
So you're in a mire of contradiction there.
Oh, well, I said I used to be a Bayesian. I don't have to answer that question anymore.
You in a generic sense.
Yeah. Yeah. So, well, I mean, my Bayesian friends are not convinced by arguments like that. And I don't think Jim will be convinced by an argument like that, because you might have reasons for preferring to put the flat prior over the space conceived one way than conceived another way. Of course, you've got to say what those reasons are, and that can be a little bit tricky. But sometimes people are able to. I mean, James thought he could provide reasons for doing so.
The Jeffreys prior is a step in that direction because it in effect defines a differential geometry on parameter space, which is based on the information matrix from the probability. And he says that is what we should put the prior on. And so he has ruled out alternative nonlinear transformation by doing that.
Yeah. But I mean, as I say, my thinking now is that you just shouldn't. I don't think it's valuable to try and pick a prior in these situations. That's my. I just don't think it serves any purpose.
Yeah.
Unless you're absolutely determined to do a Bayesian analysis.
I would agree with you.
Okay. Well, agreement is breaking out.
We have, well, let's thank Richard again.
And thank you for your indulgence.
No, we should